Okay, guys, so in this case, we are going to consider a typical exam question on our AC theory. So this is all about your AC theory. This typical exam question that you're given here, if you are to consider, it is much of your N4. So some of these questions, they are like what you just need, one or two things that you need to take from your N4 to answer these questions. So as I'm going to explain this, you are definitely going to understand even to answer another question of this nature. So this is question 2.1, the first part that we have, where we are given the voltage across a certain circuit element. There's an element that you have there, and we are given the voltage across and also the current in this element. Determine 2.11, the nature and the magnitude of this element. The nature of the element. Whenever you are given this type of a question where you need to determine the nature and of the element before we talk about the magnitude, the nature of the elements is from the impedance. Remember, what the impedance does, it gives us like the type of a circuit that you're given. That is the element that you're given. If your impedance is equal to R plus JXL like this, where you are given as a plus, it means that is from an inductive circuit. An inductive circuit, which can actually be written as R angle theta, which is a positive, okay? Our theta being a positive. As this theta represents the phase angle, as we know that if a phase angle is supposed to be an acute angle. Given our R being equal to R minus JXC, also we can tell what is happening with this, which is from a capacitive circuit. We are talking of an inductive circuit. We are talking of a capacitive circuit. Capacitive. If our Z is equivalent, so this will be a negative theta, which is a negative phase angle. Then if this theta is equivalent to R, maybe is J, then there's a 0 here. We do not have anything. It's a purely resistive. So in this condition, our R is, our Z is equal to R angle. The angle that you're given, it is at 0 degrees. When it is at 0 degrees, that is going to be a purely resistive circuit, all right? So this will be a purely resistive circuit. We're talking about a purely resistive circuit. So this is all about the impedance. So the impedance can actually give us the nature of this element. So you are going to find the magnitude of, then the magnitude later on, but before we need the nature. So we need Z. So how can we find Z? We are given an expression for the voltage, an expression for the current. Remember that our Z is supposed to be given as the voltage over the current. So what is it that I'm going to consider? I'm going to take the magnitude of the voltage, which is 800, and also the angle that is affecting this, which is the phase angle of 30, to the current, the magnitude of the current, to the angle that is affecting, which is 30 degrees. All right, remember this is omega, this one, your angular velocity, the part of the angular velocity does not affect us when calculating this Z. All right, so if you're to divide this, let us divide, remember your complex numbers in polar form, you divide the numbers. That's 800 divided by 8. That's what's going to be 800, 100. Then for the angles, if you're dividing, remember you subtract from N4. We talked about this. So that was going to give us a 0, 30 minus 30. In polar form, remember the angles you subtract. If you're dividing, if you're adding, it means you're multiplying. So this Z is equal to 100 angle. The angle is 0 there. If we take on these conditions, we are not having an angle of a positive theta where it's maybe 30 or 90. It's a straight 0. So it means we're talking about a purely resistive circuit. That's a purely resistive circuit that we are talking about in this case. So this part here, we can conclude from this zero that we can see that this is a pure resistive, all right? So it is a pure resistive circuit. So this is a pure resistive circuit that you are going to have at the end, which is the element, the pure resistive element. Why? This is at 0 degrees. Being at 0 degrees, it means it is actually in phase with the voltage. It is actually in phase with the voltage that we are given. All right. So that is the nature. This one, it is a pure resistive element. Let's say you obtained 100, then there's an angle of maybe plus 30 degrees. It means we're talking about what? An inductive, not purely inductive, but an inductive circuit. On an inductive circuit, you have to find the inductance, which is your L, and also the resistance, because it's an RL circuit that you're going to have. The element will be having a resistance and an inductor, but this one, it's purely resistance. There is no inductance or capacitance because it's at 0 degrees. All right. So we also need the magnitude of the element. The magnitude, remember, it's a purely resistive. So what is the magnitude of this? That is the resistance. So the resistance there will be 100. All right. So that is the magnitude. So the magnitude was going to be equal to 100 ohms. All right. So remember, this is impedance, which is measured in ohms. So that means that resistance is of 100 ohms. Okay, just like that. Then the time period of the waveform. We do understand also from our industrial electronics N4, we talked about this. If you're doing industrial electronics, that is, we can calculate the time, this one, from 1 over the frequency. Time, remember from your waveform, time is equal to 1 over frequency, which is also the same thing. Frequency is 1 over time. All right. So our time measured in seconds and the frequency in hertz. But we do not have the frequency. We are limited. We do not have the frequency. But if we are to cross-check here, we are given the omega, which is the 314T, the expression of a sine wave. Remember how you present your sine wave. All right, the presentation of a sine wave. If there is a voltage, it means V is equal to V max, the sine of omega t plus or minus theta or alpha, whatever that you're going to have, in this case in degrees, or it can be in radians. This is the omega times the time. So there we have got the omega. Remember, omega is equal to 2 pi f. So there is a frequency there. The omega, in this case, we are given this omega, the part that is affecting time, 314T, is 314. That's our omega, this one. So if omega is equal to, what about the frequency? Just divide by 2 pi both sides. So you've got the frequency. So frequency is omega over 2 pi. Which is the omega that we are given, 314, which is our angular velocity over 2 pi. So if I was to divide this, I was going to obtain the frequency, not the time, but the frequency. So that was going to be 49,975 hertz, which is approximately 50 hertz. You can actually approximate this to 50 hertz. All right. So we can take this now to find the time. So the time in second, which is 1 over the frequency, 49,975. That was going to give us something like 0,02001, something like that, which is something like 0,02 seconds. All right. If you want to write this in milliseconds, you multiply by 1,000, by 1,000. So you're gonna have something like 20 milliseconds. If you want to convert to milliseconds, if you want, that is, if you want to have a what? an answer in milliseconds, but this, you can just write it as it is. That is the idea there. So given a consideration, given this condition that you are given the frequency, or you calculated the frequency. From the frequency, you can calculate the time. So this is how your questions might be like. So that was it on this question. 6 marks, which is actually a lot in exam to obtain this. It's actually a lot. All right, let us consider question 2.2, which is actually having the major part of our marks, the marks that you're given there. The major part is from this. A circuit is consisting of, so we are given that there it is a circuit consisting of a coil. All right, there's a coil which has got an inductance and also a resistance. The coil has got an inductance and a resistance connected in parallel. All right, with a variable capacitor. So the coil is connected in parallel with a variable capacitor. So you can even present this way. That's 2.2. Just gonna have a sketch of the diagram, how it's gonna be like. So there is a coil, which you can even write a capacitor. You can even draw a capacitor on top, no problem, or you can even start with a coil. The coil has got an inductance and also a resistance. So that's an RL part of the coil. It's an RL circuit. But this part of the coil, we are given this part. All right, let me just present this. That's resistance, 8.25 ohms, and the inductance, which is 140 microhenries. All right, this is your coil, the whole of this part here. The whole of this part, it is building up a coil. That's a coil. It is made up inductor and a resistor. But they are saying this coil that we are seeing, it is connected in parallel with a variable capacitor. It is connected in parallel with a variable capacitor. There's a capacitor that we have, which we do not know its value. And the moment that we are working, or we are talking of a variable capacitor, guys, it means we are at resonance. We are talking about a resonance circuit. Sometimes they do not even refer to this resonance, but you see that if you calculate your XL, which is the reactance of the capacitor, comparing with the resistance, you are going to see that the resistance is going to be very small compared to XL. Compared to X, it's going to be very, very small. That is actually negligible. We cannot consider this as part of our circuit. We can even ignore it. It'll be very, 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 very small. We're going to talk, it's at resonance. We're going to talk about that. When it is at resonance, when this is very small, we're going to talk about a condition. But when it is not small, because they can give a bigger value, we're going to talk about a condition of that. But what I'm simply trying to say is that this is at resonance. Also, they talked about this later on. Calculate this, whatever, to give resonance. All right, no problem. We're going to talk about that. This combination that we are seeing is then connected in series with a resistor of 7,300 ohms. All right, so the whole of the combination, which is the parallel combination that we are given here, it is connected in series. There is a resistor connected in series to the combination, then to the supply. So maybe this is your R1, this will be your R2, which is 7,300 ohms. And the whole of this part is connected to the supply. All right, let us just consider, guys, this is just a sketch. All right, but you're supposed to draw neat diagrams. Here, I'm just showing guys a sketch of what you're going to have. So it is connected across what? There's a voltage of 380 volts with a frequency which is of 1 megahertz. All right. Calculate 2.21, the capacitance of the capacitor required to give resonance. pretty much the capacitor of the capacitance. I'm going to talk about that. If you are at resonance, you're going to think of these two formulas, actually this being of a series and this being of a parallel, which is the one that we are having. This is a parallel connection. But in a parallel connection, we are limited to something that we must test the resistance so that we verify if this formula can be used or not. This formula can be used that I stated there if our R, like I mentioned before, that it is going to be very small. If this R is very small, so we are supposed to test this. You're supposed to test first. All right. So let us test. Our R is equal to 8.25 ohms connected in series with this inductor. We're talking about the parallel combination of the circuit, the parallel combination. The resistance there is 8.25. What about XL? Because you have to compare R and XL. XL is equal to 2 pi FL. Remember that 2 pi times the frequency, 1 mega, that is times 10 to the exponent of 6, times the inductance, which is 140 micro, that is times 10 to the exponent of -6. If you were to simplify this was going to give us 879.646 ohms. Guys, we are doing electrical engineering. This resistance that we are seeing here is almost a kilo ohm. Very big enough compared to this 8.25. Very small. The 8.25 is very small compared to this reactance. Very, very small. Almost a kilo ohm. Very, very small. So in this case, our R is very small compared to what? Compared to XL. So in this case, we can neglect R when it is like that. Thus, R is negligible. All right, guys, I don't know how do you pronounce these ones. All right, but that is, it is to be neglected. You can just leave it like as it is. You just leave this part of R. So if that is the case, it means we are going to consider this formula without this R that we are saying. We are not going to have this one. This one, you use it when your R is big, like when you compare, let's say, this is 500, this is 800. These are values that are almost close to each other, but 8.25 and this value, guys, this is big. This is too much that we can even neglect our resistance. So we take this formula of a normal. This is our normal formula that you calculate, that you use when you're calculating what? The resonant frequency. So this was just to test if this formula was going to work. So this formula is truly the one that you're going to use, that the resonant frequency is equal to 1/2 pi, the square root of LC. Why are we concentrating with this formula? It is because we need the capacitance. Guys, remember the question, the capacitance required to give resonance. This formula, we have got the C, which is our capacitance. So it's either you're going to make this the subject of the formula. If you are to cross multiply, that is going to be 2 pi F in this case. So it's going to be 2 pi F. Guys, this FR is for the resonance. I'm just going to write F so that you do not confuse, all right? Then we've got the square root of LC is equal to, this is cross multiply, that's a 1. What you need is this LC, so you're going to remain with the square root of LC divide by this 2 pi F. So it's going to be 2 pi F. Then definitely I'm going to square both sides. That is LC by squaring. I'm going to remain with LC, which is equal to 1/2 pi F squared. So what do I need? I need this C. So in most cases, they are going to ask you to calculate the inductor. That will give you the inductor at resonance or the capacitor at resonance. So at this stage, that is where you find whatever that you want. You want, what is it that you want? The capacitor. So you divide by L. So you divide by L both sides. So the capacitance is going to be given by the formula 1/2 pi F squared in a bracket like this. times L. So in another question paper, I'm not going to talk about this, guys. I think you now know how to formulate this, all right? So in the same sense, we can conclude that the capacitance at resonance, or that gives us the value at resonance, is given as 2 pi f squared, times L. Also, the inductance at resonance is given by 1 over 2 pi f squared times C. So these are two formulas that you can actually consider or to memorize or to have in exam. They are going to be very, very useful at what? At resonance. Capacitance is equal to this, which is measured in farads. Then inductance is equal to this formula measured in henries. So actually, we were not supposed to even waste much of our time manipulating this if you know this part, all right? So this is it, guys. If you know that your resonant frequency is equal to this, therefore, the capacitance at resonance, like I formulated, it is going to be 2 pi f squared times the inductance. Just like that. So everything is given, or everything is there. So it's just going to substitute. So this is 2 pi times the frequency, which is at resonance 1 times 10 to the exponent of 6 times the inductance. All right, there's a squared there. Don't forget this. The bracket squared, not part of F, but everything. You close the bracket, then you square. Then the inductance, remember from our information, the inductance is 140 microhenries. So this is 140 micro, that is times 10 to the exponent of what? And -6. So this was going to give us our answer in farads, which was going to be 1,80930, something like that, times 10 to the exponent of -10. But now, remember, it is best that if you're writing these farads, you consider as maybe nanofarad, the picofarad, and so on. So times 10 to the exponent of -10, it's nearly the picofarad, which is the picofarad is times 10 to the exponent of -12. So how do I convert to the picofarad? I multiply by the opposite, which is I just remove this negative and it becomes a positive. So multiply your answer by 10 to the exponent of 12. If you multiply your answer by 10 to the exponent of 12, you are converting your answer to picofarads. Whatever that you're going to have on your calculator, it is going to be in picofarads. So you're going to obtain 180,931 if your calculator is fixed to 3 decimal places. This is the value that you have already, or automatically that is going to be in picofarads. So that is how you calculate this. So from this, you can even calculate if it was inductance, you're going to use this formula. But this part here that I was testing, it is for us to be sure about the formula that you choose on the resonant frequency there, because the actual formula is supposed to be this one in parallel. This was supposed to be our actual formula in parallel. But it follows that if the resistance is too small compared to XL, we are going to use this formula instead. Okay, so that is what you need to understand. So do not confuse this part. It is because our R is negligible. It cannot be considered. It is very small. All right, so that was it on this part. We now have the value of this capacitance at resonance. That was 180,931. Remember, this was 931 picofarads. All right, so I'm just doing this so that I can remove these guys. Remember, these boards, they are very, very difficult to work with, just that you need a space to occupy so that you also see what I'm trying to write. So like I said, these formulas, take them by heart. You might be asked on another question to calculate the inductance. They will give you the capacitor, this one. Then they will ask you to calculate the value of the inductor at resonance, or to give a resonance. So you must be careful. All right. 2.22, the impedance of the parallel circuit, the parallel combination. This one, this is our parallel combination. What is it that we consider in a parallel combination? In a parallel combination, there is one, the coil, and also the capacitor. This is making up our parallel combination. So meaning to say we can consider the coil as Z1 and this as X, which is for the capacitance. But in a sense, guys, that you're answering these questions at resonance, I want you to be careful. You can use this formula in short, which states that the parallel combination, which is the parallel for the parallel combination, the impedance, because it's at what? At resonance. So the impedance that you calculate is your dynamic resistance, the dynamic impedance. So you are going to calculate the Z of the dynamic, which is L over CR or RC, which is the dynamic impedance. That is the impedance of the parallel because it's at what? It's at resonance. Just like that. So using this formula is a straightforward formula. Just need to substitute L, everything we have. Look now, guys, I circulated this. Very sorry for that. But this is it. The inductance, that was 140 micro henries. Then we also have the capacitance, which was 180,931. That was 180,931 times 10 to the exponent of minus 12 times the resistance, which is 8,25. There we have to use the resistance. We do not we neglect it when you are calculating that part of what? Of when you are calculating the resonant frequency. That is when you talk about neglecting this. So this is your parallel impedance, 9,000. It is actually 93,790,986 ohms. Okay, or you can just write in kilo ohms, 93,791 kilo ohms, okay? Just like that. So this is what you're going to have. This is the parallel. You already have the parallel combination here there. So let us just write aside. We might need this. So for the parallel combination, the impedance was 790,986 ohms. You can also write this in kilo ohms just to save these. There's a lot of digits there that you're going to consider. But on my preparation, guys, I just prepared this with this value. No problem. No problem for that. 2.23, 9 marks, this typical question. The current in each branch of the parallel circuit of the parallel circuit. Okay. So how can we calculate this one? The current in each branch of the parallel. Meaning to say we need this one. Very so guys, yeah, if I erase, I have to erase everything. So I just mistakenly did this. No problem. So let us consider branching this into two currents of the parallel circuit. Consider this, the coil as current 1, and this part of the where we have our capacitor as current 2. This is the parallel combination. If let's say we know, because we have got this impedance of the parallel circuit, the impedance is there. If let's say we have got the total current, that is an assumption that I'm making here. Let's say we have got the total current. We can find the voltage of the parallel circuit. Because the voltage of the parallel circuit, all right, this is another question. Let us just consider this 2.23. So that's 2.23. So if we consider the voltage of the parallel circuit is simply the total current, because the total current is the one that is going to pass through here, times what? Times the impedance of the parallel. But we do not have the total current. Why focusing with the total current, or I mean the voltage of the parallel? Remember, in a parallel circuit, the voltage is the same. So if I have the voltage, I just have to divide to the impedance to determine the current in each branch. And remembering that this is at resonance. at resonance, where XL is equal to XC. So meaning to say, we already have our XC at resonance. Remember, XL is equal to XC. So it means XC is there. We have got the resistance of this part of the capacitor, where the capacitor is, the reactance is given, which is 877.646 ohms. We have this one. So by finding, remember we have the parallel impedances there for the parallel circuit. So if we have the voltage of the parallel, we're not going to have a challenge, because the current that is flowing across the coil, this one, it is the one for the coil. It is going to be the voltage of the parallel circuit over the impedance of the parallel. If it was the current 2 of the parallel, because we consider this parallel, it was going to be the voltage across the parallel, because it is the same across the parallel. But considering now the resistance here, which is the reactance of the capacitor, which is XC, we are going to calculate these currents. These are the currents of the parallel circuit. But now we are limited because we do not have the voltage of the parallel. That's why I'm focusing with this. All right, anyways, let's talk about this. We said we are going to need the total current in order for us to have this voltage. Okay, so where are we going to have the total current? That is the question now. Okay, if we consider we have got the voltage, total voltage, the impedance of the parallel is there. So if you take this parallel combination, you add to R2, what is it that you're obtaining? Because R2 is in series to this. You're obtaining the total impedance. So meaning to say, we can have the total impedance, which will give us the total current. So the total impedance is just going to be the sum of the impedance of the parallel connected to series impedance, series resistance R2. So that means from this, it was going to be 93,790,986 plus R2, which was 7,300. Okay, guys, these are bigger values. Let us just add, then we write even as kilo ohms. So this was going to be 101,090,986 ohms. So dividing by 1,000 to convert to kilo ohms, that was going to be 101,091. So this was going to change. So that's kilo ohms. At least, guys, let's work with lesser values than work with more values like this. Okay. So there I have got the total impedance of the circuit. Remember, impedance just works as the resistance. So that means we can obtain the total current. Having the total current, we can have the voltage of the parallel combination. All right, so the total current being taken from the total voltage over the total impedance from our circuit. Our voltage is given, that is 380 volts. So there we have got our voltage, the total impedance, that is the value that you just obtained, 101,091 times 10 to the exponent of 3. That was going to give us the total current in this case. All right, so if we were to divide, this was going to give us something like 0,0037 589, something like that, which is amps. So to find the total current, what are we going to do? Okay, just to write, because 0, this is too much. We can just even write as milliamps, just multiply by 1,000, which is the opposite. That was going to be 3,759. So value there that's going to change. So that will be 359 milliamps. Okay. So given this as your total current, we can calculate our parallel, the voltage of the parallel circuit. Remember, we say the voltage of the parallel circuit here is going to be taken from this formula. So that means we can calculate that voltage. The voltage in the parallel from the total current times the impedance of the parallel circuit. So our total current, this is what we got. That is going to be 3,759 milliamps times 10 to the exponent of -3. Then considering the impedance of the parallel, remember that value that we had before. So that is 93790,986. Okay, so this was going to give us the voltage and the parallel combination if you were going to consider these calculations. That was going to give us something like 352,560, which is just 0.56. So there we are done. With the voltage of the parallel combination, it is now easier for us to calculate these currents. Current 1, voltage of the parallel over the impedance that is of the parallel, because this is the current that is flowing across this branch, which is across the coil. Remember, we have got the impedance of the coil. All right, we've got the, all right, this is the parallel, the total of the parallel. Sorry, that is the one that we are given there. This is the, guys, we need the one that is affecting here the coil, not the parallel there. We need the coil. This is the total. So we do not have Z of the coil in this case. If you are to consider, we do not have this Z of the coil. So how are we going to take this part? Because we do not have the part of the coil. We are going to consider these guys to say that this is the same thing that you're going to have voltage here. And in a condition that you are working with a resonance, the Z of the coil and this XC is going to be the same. Remember, XC is equal to our XL. So you're going to take that as your XL as it is from this current. Okay? All right. This is what you're going to have, or just consider this. If you do not understand me, let me just put you through this way. We have got the voltage of the parallel circuit. So it's easier for us because we have got XC. So we can calculate, let's start with our current across the capacitor, which is our current 2. The current across the capacitor, which is our current 2, we have got XC. So it's going to be V parallel over XC, all right? That's our V parallel over XC. So that means I2 is going to be taken from the parallel voltage 352,56 over XC. Remember, I said XC is equal to the XL that we calculated before, which was 879,6. That was 646. All right. So this is 646 like this. All right. So this is going to give us the value for the current that you're going to have. In this case, I'm just going to also recheck my value there. All right, so let us check what we're going to have. You just have to be careful on your preparations, like how you're going to have this. So this was going to give us something like 0.40, right, 0.1, all right, which is amps. So this is the current that you are given from the original value that you had, from the reactance. This reactance that we are talking about, what is it representing? The reactance that we are having in this case. This is the reactance across the capacitor. Across the capacitor. So now let us consider this across the coil, having the same consideration of our XL. Because guys, this is what is happening. This is your parallel. The current is flowing here. It is a current that is flown across this I2. From the supply current that we had before. All right. But this now, if you consider that, you're going to have a mistaken. You are going to actually mistaken everything if you consider to say, this is from the total current that I have, so I can now take this total current, subtract. No. You are going to consider these two being equal. The coil, the part of the coil. All right. Remember when we calculated this, the part of the coil here, our XL, we consider this to be negligible. Like the resistance is not considered. So if you are to calculate the impedance, this is what you're going to have. All right, guys, there we're just going to have Z coil. All right, there is a resistance, so we're going to have R squared plus XL squared. The resistance there being what? The resistance, that's 8,25. All right, so they're going to have 8,25 squared plus XL, which is 877,646 squared. All right, so meaning to say there we have got the resistance that we are going to use when we are considering the coil at its own. But now because of the reactance that we are given, I mean, because of the negligence that we talked about before, I want you to see. You consider this, all right? This is going to give you something like 8. It is actually giving us 877,647, something like that, which is going to be 685. This is what you're going to have. Guys, look at what you're having. The resist, this one, it is simple. It is actually almost the same. You were not, there was no need for you actually having this. There is no need for you actually having this because it is the same. It is negligible. So you can even use this, as I was saying before, that you can just take your Z coil to be equal to XC when it is like that. But in case that you calculated, no problem, you have got your Z coil, it's you guys, it's you. It's you and your calculations. Let's say this is what you have. You're going to obtain the current across the coil, which is our current 1. The current across the coil is current 1. So the current across the coil from voltage of the parallel over the this one of the coil. So that means our current 1 was going to be V parallel 352,56 over Z coil, which is the one that we got, as you can see. That's 877. All right, guys, here, where am I obtaining this 879? This one, this is 877 here, 877. So that's 877, comma, all right, 685. Like this. All right. So this is it. If you were to divide, that's 352.56 divided to the current that you obtain, which is actually similar to the one that we had before. That was going to be something like 0,40167, which is 102 amps. This is just one and the same thing. So in an exam condition, there is no need for you to have this on its own. Just use this at resonance. That's at resonance. Remember, we are at resonance. These are conditions of what? Of resonance. So you can take advantage of this condition of resonance and to say that they are actually equivalent. Once you neglect that resistance, you can also take that consideration. So the question was to calculate the currents which are across the parallel circuit. So we've got I1 and I2, which is flowing across the parallel circuit, across the parallel combination that we are given. That is how we can play around. So as you can see, it is something that is actually of not normally that you are used to. At resonance, it has got its own properties. These are the properties that you need to take into mind. All right, so we shall have more questions, like I said before. that we're going to have as our revisions preparing for our exams, which are ahead of time. But for now, that's it. Till we meet again.